Hello everybody. Probably we are passing the most important part of this topic. Topic 13, the extra element theorem. And this morning I made one additional lecture slide, so you don't have this. Okay, so this will be attached in the post lecture slide, so you're okay. All right. Okay, so this will give you some idea, more concrete idea about the concept of EET. Okay, so this is our original model. If the GL is absent, that is the uncoupled converter model, and with this GL, this is the load coupled model. Okay, so this is the original model, not original. Originally, we are using this model. And I modified several steps, and finally, this will be converted into this form. So I call it EET, comparable model. So this is the form of EET. We used this block diagram to explain the EET. First, this is the original model, and this is the voltage, this current. Okay, so I take out this here, and I replaced with this symbol, with this current source symbol, because you are interested in this, the input impedance, then input is this one, output is this one. Okay, so for that purpose, I take out this, like this is the current source, and this is voltage, and this is the same thing, exactly same thing, and I stretch out this one, and I pushed something into this box. So VO is here, IO, it was here, but IO is moved to here, which is the same thing. Okay, so I put everything inside of this box. Okay, then I blocked this box. So inside the box you are not seeing anything, but inside the box we have this. Okay, and this is taken out, and I assigned A prime at these two nodes, and this is the input, this is output. Okay, and we are interested in this input impedance of this load coupled converter. So transfer function of our interest is, this is the input, this is the output, and this will be considered as what? Extra element. And one thing is IO. IO is some time varying variable, but here IO is constant. Okay. So then this is the same as our notation. We used this to establish the EET. Okay. So this is the same thing actually. So the conceptual perspective of this uncoupled converter and the load coupled converter is exactly the same as the basic concept of EET. Okay? So when I was developing this concept of uncoupled converter and the load coupled converter, source coupled converter, and fully coupled converter, I didn't know the EET. Okay? But somehow I was thinking about this concept, and later on I found the EET through the paper, Dr. Middlebrook's paper, and I found out this concept is almost the same. Okay? So, but here we need to separate between DC and AC. So, because this EET is valid only linear time invariant system, but this converter, PWM converter, is something else, time varying nonlinear system. So this is the linearized model. Because of that, we need to specify this. Okay? But in general, there is no limitation in the circuit variable. It can be AC or DC, AC plus DC, very large, very small. It really doesn't matter because this is the linear circuit. So the superposition principle and the proportionality property are there. Okay? So everything remains the same. Okay? It's amazing, this concept of this uncoupled converter and the load coupled converter and the basic setup for the EET. Okay, Middlebrook, he used this setup to explain the EET, and the original version of EET, I said the Hendrik Bode proposed that maybe 60 years ago, but the name was something else. That was nameless. Okay, and Middlebrook arranged in this manner, and he named this theorem as external element theorem. So this is known. So after that, it is known as Middlebrook's EET. Okay, so this is a very natural way of thinking something. Okay, so the concept we discussed in the previous lectures, uncoupled converter and coupled converter and unknown GL. Okay, so we used the current source here, ideal current sink, then GL is infinity. So that concept is exactly same as evaluating the transfer gain with GL G opened. Okay, and after that we are attaching the impedance, but this DC variable is something else, something separate from this concept. So this model, this approach is only valid for our case in the vicinity of steady state operating point of our converter. But in this original form, this is valid regardless of the magnitude and the nature of input and output variables, because this is valid for the older linear time invariant system. Okay? So this will be the inference your understanding about the EET. EET is something strange, something weird, not that. Okay? So this is a very natural approach for the practical application. You have some equipment or some instrument, and somebody is attaching something else. Okay? Then you cannot analyze everything combined all over again. That is impossible actually. Okay, so this is the approach you can use for that situation. That is so this concept is applicable universally, I think. Okay, regardless of the area of engineering. Okay, so can be used some mechanical things or some in electronics, microwave, circuit theory, and anything. Okay, this is a very basic concept. And additional comment is about this null driving point impedance. Okay, so maybe you think very strange or not comfortable with this output null condition. Okay, we assumed this our voltage is 0, then I should be 0. Then this is the only one current pass. This I should be 0. Potential here is 0. Then potential here should be the 0. Then incoming current is this one. And this current is 0. That should go this way. So I prime should be this one. So we have a relationship between this. Okay. So using this or under assumption of output null condition, we evaluate, we find out relationship between this variable and this variable. Okay, but you don't have to find this relationship. Okay, if for any circuit, for any linear time invariant circuit, you can create this output null condition. Right? Think about this. This is a linear time invariant system. So we have two inputs here. This is the input. This is the another input. Okay. You activate this, and this one is dead. You generate some current. Okay. So suppose you have this current is 1 amp. Then you eliminate this, and you activate this, and you generate somehow the current of -1 amp. They cancel. I is 0. That condition is, you can always find that condition. Okay, so in here we used this condition and we find out this condition. Okay, that is a 1A. Okay, but you don't have to find out this condition. You assume this is established with some pair of this and this. Okay, their relationship is adjusted to make this one 0. Okay, there is the comment. Okay, the output null condition is always created by selecting these two input wisely. For this case, this is the case. This is the condition for this. Okay, but this knowledge is unnecessary. You don't have to know this. Okay, the only your interest is to evaluate this null driving point impedance. For that case, assume somehow this condition is created, then this is 0, then this is connected here, this is 0, then you are looking this circuit through this opening, then what you are seeing is just R2. So this is the R2. Okay? Suppose this UI is 1 volt and R1 is 1 ohm and this current is 1 amp. Okay? This current is 1 amp. Okay? So you are applying 1 amp here because we know this condition. So you are applying 1 amp here, then 1 amp is going to this way and coming back, and this is 1 amp, then it circulates. Okay? This is the only possible solution to create this output null condition, and this condition is always existing if you select the ratio of this one becomes this one. Okay? So there are infinitely many solutions. Okay? 1 is the solution, 2 is the solution. If something this pair satisfies this relationship, then that create the output null condition. Okay? So when the Dr. Middlebrook, first time he was publishing this, he used this term, null double injection. Okay? So you are injecting two signals, one here and another one here, to create this output null condition. That is always possible. Think about the superposition. Okay? You do one input, you create some value, and with the other variable, you create the negative of that, then output becomes null. Okay? So this word null double injection is very informative. Okay? And think about the superposition. Okay? The way of thinking this problem is very similar of the deriving the Thevenin's equivalent form. Okay? Everybody knows the Thevenin's equivalent form, but very few people knows to verify that. Okay? In the most textbook, they are just showing this. This is the rule. Okay? This is the Thevenin's rule without any proofing or any additional comment. So the formal way of proving the Thevenin's form is the use of superposition principle, very similar to this. Okay? It's not easy to figure that out. So many textbooks and most of professors, they don't mention that. Where that comes from? That comes from the superposition principle, very similar to this kind of thinking. Okay? This kind of reasoning. So this is very important. But later on, we will be using this condition without thinking about this condition. That is fine. There is a case. Then we don't have to know that case. Okay? Then just use the result of that. Assuming the output null condition, we figure out that null driving point impedance. That is the second comment I want to make. And finally, this one. This is a very important example, and I added something here. Okay. Again, this will appear in the post-lecture slide. Okay, just listen to me. All right. So, for the clarity of discussions, I draw this. This is the load-coupled converter, and you are interested in this input impedance of this converter, which is transfer gain from this input current to this input voltage. Okay? So this is the general equation for that case. This is the EET formula. So for this special case, H is GIL, input impedance of this load coupled converter, with this G present. Okay? And H infinity here is, this guy is gone. So this is the input impedance of uncoupled converter, but DC information of output current is embedded in here, okay? And this one, this zeta bar is null driving point impedance, which is the output impedance of this converter. We went through this, okay? So that is the regular output impedance, GOU. OU means this is output impedance, U means uncoupled converter. So we know this, right? Because we designed this and we analyzed this because we have complete knowledge about this converter. Because we are designing this, everything is known. We designed the control loop, everything, so we know everything, okay? Then we can evaluate this output impedance of this uncoupled converter. You can evaluate or simulate or measure with current sync load. Then this is driving point null driving point impedance, and this is output impedance of this uncoupled converter with input port open. Okay, so this is something special. So probably we cannot measure this, but still we can simulate this or we can analyze this. Okay, so this are known. So we know this H is this H infinity is known, and this is known. This is known. Okay, so later on we don't know this. Okay, when we are designing and analyzing this, those load structure is not existing, but eventually that information will be available, and maybe we can ask vendor, the guy supplying the load subsystem, give me the input impedance curve. Okay, we can request that, and that is obtained. Okay, so before that we analyzed this our system, and we obtained this H infinity. This is what the input impedance of uncoupled converter, and we find out this is null driving point impedance, and this is driving point impedance. So these three information, this one, are available in advance. Okay, and later on this guy is coming in, so we overlapped this curve onto this. Okay, then you have this kind of situation. Then how the input impedance of load coupled converter will be formed. Okay, so for the wide range frequency ranges, they are the same as this uncoupled one, but some frequency range there is just some modification. That modification is predicted by this equation in this manner. Okay, so I divide this range and this frequency range, this range, and 5 ranges. For example, this is a very complicated case. Okay, most cases are much simpler than this. Okay, this is a complicated case. Okay, if you take a look at this area, this region 1 and region 3, region 5, G is larger than this one and this one. Okay, magnitude of G is larger than this one and this one. Then in this equation, you ignore this, and you obtaining is this one. That means in these three areas, this H is following H infinity very closely. Okay, there is just some deviation around here, but that's not important. Okay, you are not worrying about that. You want to know the general shape. Okay, so in this region 2, then this guy is bigger than this. Okay, then this term is stop talking. Okay, so this is ignored. So this guy is coming here, but this G is here, is much lower than this. We ignore this. Then this is the expression of H using H infinity and 2 driving point impedances. So this is a linear scale and log scale. The magnitude is added, okay, in the Bode plot. Then this is the original plot here. Then there is some addition of this much. This much is actually this is this minus this. So that means this zeta bar is here, and at this value, you subtract this, what you are obtaining is this much. So this area of this triangular shape is this term. So this is coming in the numerator, so it will add up. So we have some peaking, bulging here. Same thing, okay? We can argue same story here, but this guy is coming from the denominator. So it is a denominator. So we have subtraction, then there is some dipping here. So this goes down this much, okay? Understand this, right? So this is the essence of using this EET for our case, okay? There are many other applications, and this is just one simple applications, but this is, I think, this is the most important applications, okay? Something, you need to calculate something, some tedious thing, then you can calculate almost very complicated one. So many people think it is almost impossible to derive the transfer function of something, but EET will allow us to do that, but there is one application, okay? We are not interested in that, okay? Maybe somebody else is interested in that. And another application is, because this is in this form, G is here. So suppose G is changing from the normal value with some tolerance, then sensitivity of this entire transfer function to this one particular component can be easily evaluated, because this general form of this EET equation, there is another application, and there are many applications, okay? So this is the very generic tool for the circuit or system analysis, but it is not well known yet, okay? They know the name of EET. If we go to the YouTube site and hit EET, there are a bunch of examples, very extremely simple, basic examples, which is most likely used, okay? So this is the way of using this, okay? So we combine this EET equation with the asymptotic approach we practiced in the previous lectures, and the Bode plot technique, which is inherently graphical, and the asymptotic plot, magnitude plot, and the phase plot of the Bode proposed. We combine them all together, so then we can analyze the very complicated system without any numerical calculation, okay? Very minimal analytic work. You can understand the behavior of the system, okay? All right, so that was the lecture 1 of EET, and lecture 2 is EET application to load coupled converter. I already presented several examples, okay, to explain the concept of EET. So at that time, in the previous lecture, I used the load coupled converter as a simple example. But in this chapter, in this lecture, we not completely, the complete story is coming later, but somehow we further analyze this load coupled converter using the EET, okay? So this is the diagram of load coupled converter. First, this is the uncoupled converter, and this is the small signal block diagram of uncoupled converter. So I found out this is necessary, okay? So I/O is time varying function, okay? But here, I/O is fixed DC value. This is for the buck case, this is the inductor current, which is the output current, okay? And this is the current sink, and this is what? This is the small signal current source. They look the same, but they are different. One is current sink. This is the AC disturbance source, sinusoidal current waveform. Okay, so different. And load coupled converter is this one. So same thing, but we have this GL is coming here. So we apply the EET to derive the for transfer functions of this converter based on the assuming that we have complete knowledge about uncoupled converter, which should be true. Okay, we designed this, we built this. Okay, so we know all the information. And this, all the information is available. Okay, that is our fundamentals. And here I'll explain this relationship between this is input to output transfer function of load coupled converter, and this is input to output transfer function of uncoupled converter. They are related through this EET equation, and how to find out this. If we find out this, and problem is finished, right? Because the GL will be available eventually, and this is the small signal model for that analysis, for that EET analysis. And I made a small modification here. So this is UX, and UX is going in, and it comes back, and UI. Ratio between UX and UI is loop gain. Okay? So loop gain is the most important transfer gain in the feedback controlled system. So to analyze this is something additional, but only you are interested in input to output transfer function, input impedance or output impedance. You assume this is 0, but they are directly connected. Then you go back to the previous model. Okay. All right. And the G was here. The ET, G is here, and that ET is replaced with current source. Okay. We introduced this concept when we are verifying the EET. So this can be this is the location for the G, okay, and this is current source IT, VT, and we will be evaluating relationship between VT, IT with different conditions. Okay, input is 0 or output is 0. If you are interested in particular transfer function, so once the input is 0, and next time the output is something like that, then you can evaluate this, right? But this was, the G was in the output side of this converter. So what you are seeing is basically this is the output impedance, okay? This is output impedance because you are looking this system at the output of this converter. So eventually this driving point impedance and the null driving point impedance becomes the sum for output impedance. That's obvious, right? Because this was the ET, GL was originally located here. So I wrote down here, and this is the equation for the ET. Okay. First, let's take a look at this one. This is the input to output transfer function with GL is here. GL is not infinity, but this is the input to output transfer function with GL is infinity uncoupled converter, and this is the EET equation. And simply we need to evaluate this. Need to evaluate zeta bar and G bar. Okay. So when evaluating zeta bar, you are evaluating ratio between this and this, which is this is null driving point impedance. So for that case, this input becomes output is 0, right? For the null driving point impedance, output is 0. For the driving point impedance, input is 0. Okay, that comes from the definition of EET. We used that definition in verifying the validity of this EET. Okay. Another thing is this is the VO, this is the VT. They are the same. Okay. And this one is the same. This one is also same because this is grounded here. This is reference to the ground. So this voltage, they are the same. If one thing is 0, then automatically two other things are 0. Okay. So by the definition of this, when you are evaluating this null driving point impedance, output of this transfer function is 0. So this one is 0, then VT is 0. If VT is 0, this is 0, then zeta bar is 0. Okay? You don't have to calculate anything, just to think about it. Okay? Just think about it. Remind the definition. Then this is 0. Okay? And second one is G bar. is this one, ratio of these two, which is the impedance looking the system converter through this opening. Then Vs, this is the input of this, not input of this particular transfer gain of our interest. Input is 0. So this is just showed it, and you are looking at this converter at the output. That is the regular output impedance of uncoupled converter. Okay, so result is this. Okay, so this is the audio susceptibility or input to output transfer function of uncoupled converter times 1 divided by 1 plus this one. Okay, all right. This one output impedance. Okay. I draw this. Okay, this is GOU. This is a GOU. Okay, so this is a graphical representation of the GOU. This one, and the output impedance of this load coupled converter is definition is ratio between this one. This IO is input and this is output. So IO is input. This is output. And the GL is not infinity, GL is present. Then this is the linear system. So Vs is 0. So this is showed it. And we don't care about this. Okay, we are not analyzing loop gain. We are analyzing the output impedance of load coupled converter. So this is the equation. Okay, so first you need to evaluate this. And definition of this is ratio between this. Okay, same as the impedance looking into this condition with this slot, okay, looking into this slot with the condition output of this transfer function, transfer gain is 0, okay. So VO is 0, then this one is 0 because they are the same variables. So again, this zeta bar is 0, okay. And this one, G bar is ratio between this, and the condition is IO is 0, but this is the redundant. So it really doesn't matter. So this is 0, then you just take a look at this and find the ratio between this and this is nothing. So this should be removed to evaluate this. So this information is just redundant. Okay. So IT is not 0. So that is the output impedance of this one with this Vs. Vs is 0 here, okay? From the definition, Vs is 0. This is a regular output impedance, okay? So in these two transfer functions of the load coupled converter, so this ratio is commonly appearing here. The ratio GOU divided by GL appears as a common factor in these two transfer functions, and this will appear again and again. So we are interested in 4 transfer gains, and all of them contains the ratio of this. So this is a very important quantity. Okay. Later on, we assign special name for this. But now just you remember this term will come out again and again. And this is the diagram to evaluate the loop gain of this load coupled converter. So when you are evaluating loop gain, this is not infinity, and this is 0, showed it, and this 0 opened. Okay. For that case, this is excited, so this is not 0. Okay. So Vx is here, it goes around and come back here, Vy. So ratio between Vy hat means small signal AC, sinusoidal component, is loop gain. This is the loop gain of load coupled converter. Relationship with this loop gain of uncoupled converter is shown here. And then again, we just evaluate this and this. Okay. So first one, so we are trying to find out the ratio between this, and condition here is output of this transfer gain is 0. So Uy is 0. If Uy is 0, this one is 0, this one is 0, this one is 0, this is 0, zeta bar is what? 0. I told you the 0 will come frequently. Okay? So many cases there are a bunch of zeros. Then make this problem very simple. Okay? That is the nature of the output of our transfer function is here, and this the point, the slope. You are measuring the driving point impedance share this point. Then we have many zeros, okay, automatically. So we have 0 here. And this one, G bar, is driving point impedance when evaluating this input of this transfer gain is 0, okay. So Vx is 0. This means what? This is 0. What situation that will happen? Feedback is open, okay. So this is a feedback is disabled, or this is the open loop. So we are measuring, we are seeing the output impedance of this converter with this feedback is open. Okay? So I use the symbol GOU star. This is the GOU with feedback is open. Open loop output impedance of uncoupled converter is GOU star. Okay? So rule is this one. Okay? Rule here is this one. But GOU star is something new. Okay? So we want to replace this with GOU because GOU divided by GL is common factor. Okay? So we want to find out some other expressions of GOU star in terms of GOU. Okay? This is very important step. That is this one. Okay? So this is the converter, this is the uncoupled converter, and this is the uncoupled converter where this feedback loop is closed. This is a regular output impedance, and this is the output impedance of uncoupled converter with feedback loop is open. Right? So this is the GOU star and the GOU, and relationship between them is obvious. Okay? In the controller theory, closed loop transfer function is open loop transfer function divided by 1 plus Tm, right? Tmu, okay? So this is uncoupled converter. So we have U everywhere. So relationship, this is the open loop output impedance of uncoupled converter. This is closed loop output impedance of uncoupled converter. And relationship is this one, okay? This can be proved formally using some theory. To prove this, we can use EET once more, okay? But that is unnecessary, okay? You accept the knowledge from your control theory, regardless of the professor who teach it. If you accept this, okay, closed loop transfer function is open loop transfer function. Same transfer function divided by 1 plus loop gain, 1 plus Tmu. Then you have this, okay? Then you replace this GOU here, then you have this equation, okay? So this equation is something different from the previous one. GOU divided by GL is here. You have some additional term, but that is coming from this, the conversion from open loop transfer function to closed loop transfer function. That is okay, okay? So this is the expression for the loop gain. And this is the input impedance of load coupled converter, uncoupled converter, and we went through this. Okay? In the previous lecture, when I was introducing the basic concepts of EET, I used this as an example. So 4 transfer functions are all identified, and that are summarized in here. Okay? So summary of transfer gains of load coupled converter. So this is uncoupled converter, closed loop uncoupled converter, and this is load coupled converter, closed loop load coupled converter, and the relationship between this and this and this, okay, is shown here. Okay, it's better to swap the position of this. Okay, so assume this one comes first, then this we went through this, and the GOU is just regular output impedance of uncoupled converter where this input port is shorted. So this is the basic definition because of the superposition principle, right? And this one, you have this, okay, GI, and you have additional term, GOU prime is this one, okay? Something strange, okay? The input is open, and with that condition, we simulate this, or we analyze this, there is GOU prime. GOU prime is coming here. And GOL is this one. GO is here. And the TML is this one. TML is TMU. TMU is appearing again here. And we have our friendly ratio. Okay, GOU divided by GL. So every term has this one, and this one, this one, this one. This is very important. This will be named as minor loop gain in the next section, lecture. Okay, that is very important. But now you just remember, so this is appearing again and again. Okay, so this is the summary. Okay, so just remembering this is enough if you understand the story behind this. Okay, finally you will be using this to analyze the load coupled converter. Okay, assumption is you have the complete knowledge about this and this and this are available. You can simulate, measure, or analyze that. Okay, so they are accessible for the analysis. GL is something else. GL is coming later, so that is not controllable. Somebody else will provide that. Okay, this is the example. Probably you don't have this slide. I don't know. Maybe you have. Okay, so this is I'll show you the simulation example of the using the result of the EET to predict something or to interpret the result of the simulation. So this is the boost converter followed by this buck converter through this line filter. Okay? So line filter is very important. Line filter must be there for two purposes. One is current filtering. The other is it provides some potential. It prevents some potential stability problem. So this line filter is very useful device. Okay, circuit component, line low pass filter. I said this is very mysterious device. Okay, this one and ideal op-amp, they're very useful. Okay, and output of this is 48 volt. Input is 24. Output is 48, and DC link current is 4 amp. So this times this is same as this times this squared divided by this. Okay, same power. So we are assuming the power loss is 0 or very small, can be ignored. Okay, so this is current mode controlled boost converter and current mode controlled buck converter. Probably I provide the PSIM model for this, but this one is not working in the license-free version of PSIM. Okay, there are too many components or node count, so it's not working. You need the professional version of it. Okay, but you don't have to buy that. There are many illegal copies abandoned around. Okay, every lab has at least one. Every student has at least one. All right. So I designed this filter. Okay. I designed this filter with my best knowledge about the entire story. Okay. So this is the good design, and with that, I compared the output impedance of this one without this. Okay, with the current sink here. Then I simulate the load impedance of this one, which is combination of this filter stage and this downstream buck converter. So details of this converter is not shown here, but it has complete details like this, current mode controlled. Okay, and here this is the load impedance. Simulate here this one, and this is output impedance here. Okay, so there is overlap. This much of overlap. We have seen this overlap in the previous lecture. Last slide showed something similar to this. Okay, that is that. Okay, so this is intended. I intentionally introduced this for the some purpose, some benefit from this line filter. some good thing will come out with this overlap. So this overlap is intended and constructive overlap. I introduced using my best knowledge about this. Okay, I'm teaching this, so I know all about this story. So this is very good practice. Okay, and this overlap can be controlled. This one is fixed. This GOU is fixed by this upstream converter, but this overlap can be controlled by adjusting this parameter. This parameter, this is nothing. Okay, this is the ESR of something. This is required for the damping of this. But by controlling this value and this value, you can adjust this GL, and sometimes you can have this kind of GL. Then you have large overlap, and somehow I introduce this much of overlap. Okay, and this overlap is here. Here we call it this interface A, and the other one is interface B. Okay, so impedance comparison here is this one, and impedance comparison here is also important. Okay, but this impedance here controls impedance there, and impedance here, impedance overlap here controls loop gain of this, performance of this, and the impedance overlap here determines the quality of this DC link. This is DC link. There are additional load subsystems connected in parallel. Okay, so if some disturbance is coming in, current disturbance is coming in to this DC link, some transient response will occur here. Okay, that can be controlled by controlling this overlap. So by single design of this line filter will provide the governs the dynamics of entire system. Okay, so if you design this optimally, you can have optimal performance of this DC link and the whole system all combined. Okay, that's my approach to tackle this problem using EET. Okay, EET allows me to do that. Okay, other tool is impossible. Maybe some case-by-case simulation will be possible, but you cannot explain your result. Why that kind of result must be come out will be the big question. Okay, and the people will attack you. Okay, and they will ignore your work. Okay, so you need to have some solid background about this. Okay, I think I said what I want to say here. Okay, and okay, I want to finish up with doing this. And this is the PC model. So seeing this is also helpful to understand everything. Okay, so simulating this is this one. So this is a downstream converter, current mode controlled buck converter, and this is the filter stage, and this is the setup to simulate the input impedance of this one combined with this, which is the GL. Okay, so buck filter plus buck converter produce the GL load impedance, and this generate the output impedance of uncoupled converter. So this is a current sink, and this is set up to simulate the output impedance of upstream converter. Okay, so we are using this all the time to simulate the input impedance and output impedance of something. Okay. Okay, I think there is a technique. Suppose this system is working, okay, and you connect something, some impedance analyzer with some auxiliary circuit, then this one will be this one and this one will be measured, and it will automatically generate the experimental plot, something like this. Okay, that is very useful. Okay, then you can, the dynamics of the system. If there is some problem, this indicates where the problem is coming. Okay, so that information is very useful. And one of my colleagues, when I was studying in the United States, okay, that kind of technique we developed in our department. and we did some experiment in NASA. There is a many research center. So one was called the Lewis Research Center. We were doing some big project with that. We went there and we measured this one, and we analyzed that. But I was trying to find out that record, but I cannot find it. Okay. I threw away the most of my stuff when I was retiring this university. At that time, I want to forget about everything about this university, so I throw many things. Okay, so that is gone, right? But I remember there is a technique to measure this thing online, which is very, very important, very valuable technique. Okay, then this is the simulation result using this. Okay, using this setup and the simulate the everything with everything integrated. So this is the loop gain comparison at the inner phase A. So this is the GL, GOU. We have this much of overlap. Okay, we know this from the previous analysis. AUL, input-output transfer function of load-coupled converter. This is the input-output transfer function of uncoupled converter multiplied by this. Okay, so we are comparing this because this is appearing here and here. So this is very important. So below this frequency, GL is much larger than GOU, and this can be ignored. Then AUL, AUU, they become same. Okay, AUL tracks AUU up to this frequency. So we have this. Okay, they are the same, almost the same. And here, after this, they are the same. Okay, in between, they are different. Okay, so we have some deviation here, okay, and there is a deviation, but deviation is coming here. Okay, during this band, this frequency band, GOU is larger than GL, so this is ignored. Then AUU divided by this one. Okay, so this is coming in the denominator. So you are subtracting this much. This area is GOU minus GL in terms of their magnitude, which is this. This area is this one. So this one is coming here. So this area should be the same, approximately, at least. Okay, and there is some deviation here in between, here, and there is a peaking. There is a small peaking. We can predict this peaking, and the frequency of the peaking is same as this frequency. Okay, so maybe this we denote as G1, omega 1, omega 2, and this frequency is omega 1, omega 2. Okay? The magnitude of this peaking can be predicted from something, from this GOU divided by GL. So that story is coming next topic. Next topic consists of 6 lectures. Okay? So during that lecture, that story will come. Okay? So we have a complete story, at least for this case. Okay, next one is this output impedance. So output impedance expression is this one. So this formation, shape, structure is the same. Okay, so for the same argument, this area is the same, and this is the peaking. It's controlled by characteristic of this. Actually, phase characteristic of two curves at this point. That story is coming later. Okay. This loop gain characteristics. So this loop gain characteristics, this is different. Previously, GOU and GL, ratio of them was apparent. So now we have this additional term. Okay. Still, if this one, GOU is larger than GL, then you have this. GML is this one. This is GMU, loop gain of uncoupled converter. minus is coming in the denominator. You ignore 1 because they are large. Then you multiply this. Then this is GMU plus this is A. Right? So this is A. So A is coming here again. So this is, so we analyze this in detail in the next topic. Okay. So let me postpone discussion about this, but you can analyze everything. This is the loop gain of the TMU and the loop gain of load coupled converter. We can analyze why this thing happens. Okay. One thing, a pattern is this one. So this is same as this. Okay. This shape is same as this. And at this point, this omega 1 point, G, this ratio is 0. Okay. So A is 0. They are the same. Okay. So at this point, magnitude of GL and GOU, they are same. There is what? 0 dB. Okay. There is unity, 0 dB. So this becomes 0. Then TMU minus TMU is 0. Okay. So loop gain, TML, is crossing 0 dB at this point because this is 0. They are same. Then this becomes 0. So it's approaching to 0, not quite 0, but very close to 0 because this is 0 and they are same thing. You are subtracting TMU from TMU. Okay. So third, no, exactly, not exactly. So it can come here, but with some deviation, it is just approaching 0. Okay. So at least this can be explained by this, and other shape can be explained to something else. You need some analysis using EET. Okay. So we will be using EET many times for this topic. So the tool we're going to use is EET. Okay. So EET provide all the necessary information for us. Okay. Input impedance is the equation. Okay. So this is the friendly ratio of the two impedances, and the GOU prime is something strange. For many cases, this GOU prime is smaller than this, much smaller than this. So this can be ignored from the beginning. Many practical cases, there is a case which does not satisfy this assumption, and we'll analyze this full detail in later chapters, later sections, later topics. But now assume this can be ignored because this is dominant. This condition prevails for all frequencies. Then this will be gone. Then you have this. Okay. Then this is addition because it comes in the denominator. So we have this addition, and this area of this should be same as this. Shape is different because this is not a straight line, something strange. Then we have this one, and there is some deviation. Later on, we'll explain the reason of this. Okay, so this is some introductory analysis. Okay, so with this, you will see the use of this EET in analyzing the transfer function of this load coupled converter. Okay. If you have transfer functions, you can predict the time domain behavior of this one, or this one. This one is much easier. Okay. So you have this type. Okay. Probably you can extract the transfer function of this output impedance of load coupled converter approximately with good reasonable accuracy from this graph. Okay. And from this graph, we directly predict the transient behavior of this output voltage, step load, transient response of output voltage of the load coupled converter, which is, for this case, there is what? Link voltage. Okay. So this is the output of this converter, and this load impedance is in parallel with this. So that transient response will be the transient response of DC link. Okay. So I can sketch this very accurately. So this will be step change will be like this. there is some oscillation at low frequency. So this is a peak. Okay, there is some peaking. So from this peak, you can predict this kind of behavior of V-link, transient response of V-link. And this oscillation frequency is omega 1. So this frequency, oh, this is not good. Okay, so, and this is the oscillation frequency, right? So this is omega 1, okay? And there is another bulging here, omega 2, okay? Then think about this. This is coming at higher frequency, and this peaking is small. So this overshoot, undershoot will be smaller, but frequency will be very fast, okay? So it will show second one, something like this. Okay, this frequency is fast because omega 2 is much larger than omega 1, and the total response is sum of this one and this one, and you will see this here. Okay, so this low frequency response plus this high frequency superimposed on top of that. Okay, so if you measure the transient, step load transient of DC link, you will observe this. Okay, without this knowledge, you will be wondered why this is coming out. This should come out. You cannot avoid this because of this shape. Okay, so this response is very different from the response of uncoupled converter, because the output impedance of load coupled converter is very different from this uncoupled converter. So this should come out. Okay, this is something not surprising you. This is a natural thing. This is what you should expect. Okay, this one. All right. Okay, let me finish this up. Okay. This is also very important. Okay. The situation is this. So we have upstream converter, and previously upstream converter there was a ideal DC source, but in here there is ideal DC source, and this is the one filter, in filter. Okay, so this one has upstream converter has in filter in front of that, and that's connected this downstream converter with line filter. Okay, so there are many interface. So focus on this one. Maybe this is interface A now. Previously it was something else. Interface A is here, B was here, but now this is interface A, and this is interface B, and the interface C maybe here, but we are not paying attention on this. Okay. And GIU is this one. So input impedance of upstream converter. This is minus R characteristic. Okay, we went through this. We didn't derive this. Deriving this is very challenging. We needed to use EET here. Without EET, it is almost impossible to derive analytical form of this. Okay, so I said that time at low frequency, this becomes minus R, and it goes up, and this is the loop gain crossover frequency of this converter. Okay, that will be apparent if you understand the derivation of this GIU. It's not easy, okay, but you can do it, okay, through this lecture, right? Then this is GIU, okay, GIU here, and we are comparing this output impedance, load impedance at this interface B. So this is this one, and this is the impedance comparison of interface A. Okay, so interface A, we have load impedance here, and there is two different impedances. output impedance of upstream converter with this showed it with this opened, so that was GOU and the GOU prime, and we overplot this impedance and this impedance. Okay, three impedance here. Forget about this now. Okay, forget about this. Previously, I said this GOU prime is much smaller than GL here. Okay, this is the normal case. This is not that case. This is the special case. So I'm talking about the special case. For this special case, this impedance has some overlap with this in this area. Okay? Okay. And expression of this GIL is this one. Previously, we ignored this, but we cannot ignore here because GOU is here, and in this frequency range, the GL is larger than GOU. Okay, so this part is start talking now. Okay, so then this overlap, this one is coming in the numerator. Okay, so we have this overlap. This overlap is coming in the denominator. So this is here. So this is the input impedance of open loop, uncoupled converter, and GIL is input impedance of load coupled converter. Then GIU will be boosted this much, okay? Because it is coming in the denominator. And in here, this one, GOU prime is here, so we have overlap this much, but this is in the denominator, this is in the denominator, then this will drop this much. Okay? So original GIU is this one, which is this one, and output impedance of this one is this peak. Here we have in this region, the input impedance shows negative resistance characteristics, and we have overlap here, then this converter becomes what? Unstable. We have seen this, okay? So this becomes unstable, then whole system becomes unstable, okay? So without this filter, without this filter, GIU, without this load subsystem, this maybe there is a current sink, then that converter, upstream converter alone is unstable because of this impedance overlap, bad, unstable impedance overlap. Okay. Now there is a load subsystem. Then you have this much. This increase the input impedance of load coupled converter at this frequency this much, and this will reduce this much. So we have boost this much. You have subtraction this much. Then that difference is that increase. Okay. So this magnitude of this minus magnitude of this. So this one. Okay. No. This minus this is this one, which is this one, and this will be increased up to this much. Okay. So with load subsystem, load coupled converter input impedance will be something like this, okay? And the output impedance of this, the in filter, was this one, so there is no overlap. System becomes stable. Previously, it was unstable, okay? This load subsystem is stabilizing the entire system, okay? So this is the stabilizing effect of load subsystem. Original system, upstream converter, was initially unstable, okay? Then by using some technique and designing this, and then you can stabilize this one, so you can stabilize the whole system. That is the stabilizing effect of load subsystem. Okay, that is available because of the impedance overlap here. Okay, previously the people they think the overlap should be avoided. They try to avoid the overlap as much as possible. That was the bad approach. That makes the system unstable. Many cases, okay. So having overlap will stabilize the system. That was the this case. Okay. So this is the propagation of dynamic interaction. So it was unstable, and the dynamic interaction is occurred here, and the interaction in downstream is propagated to the upstream. Okay. So title of this lecture slide is upstream propagation of dynamic interaction. Okay. So this is one example. I have another example. Okay. So this the impedance overlap at the load or this link can be used for something good. This is one example. There are several good examples. Okay. All the benefits are possible by introducing the intended overlap at the output of converter, junction between upstream converter and the load subsystem converter. That was something new. People didn't know that in the past. They approached the opposite direction, the wrong direction. Okay. Okay, we stop here. Maybe next week, probably I need to repeat this page. Okay, so I repeat this page, and I have another example, and we move to the source coupled converter case, right? Okay, we have 5 minute delay. Previously, we finished 20 minutes early, so 15 minutes is still left. All right. Okay, thank you. Hi, everybody. In the last lecture, we stopped the last part of that lecture. So I think it's better to review this lecture slide. And this lecture slide contains very important information. And the situation is shown here. You have two converters here. And this upstream converter has in filter. And it has the voltage source. So this is kind of source coupled converter. But this is the load is uncoupled converter. So we may call it uncoupled converter. And there is another converter. And there is a intermediate line filter. So they are connected now. But assume this is disconnected. They are separated. Then we will have this situation. So this is disconnected. So system is not working. So for the operation of the system, we need to have the current sink. Okay, so this is current sink. So this is uncoupled converter, even though there is some source impedance. Assume this is uncoupled converter. So we use notation of GIU, and U stands for uncoupled converter. And the downstream converter is derived by voltage source, ideal voltage source. Right? So this downstream converter. So they are separated, and consider only this part. And we are comparing the impedances here. We defined this place as interface A. So we have two impedances at the interface A. One is the source impedance of this infilter seen through this point. And the other one is input impedance of this converter, actually upstream converter. And we have notation of GIL. GIL is the input impedance of this converter with this connection. So it is disconnected. So this is the GIU. Okay. So GIU is input impedance of converter. Regulated converter has this kind of input impedance characteristics shown in this black curve. So we know this at the low frequencies, this behaves as negative resistance minus RIC, and the value of RIC is just the ratio of voltage here and the current through this path. So minus RIC is up to here, and at high frequencies it goes up. There is just some drop at the loop gain crossover frequency of this converter, but it's not shown here. That can be minimized with some control scheme. So this is the minus R, and this is the plus 1 slope. Actually, this is the inductive behavior is appearing. The slope is actually determined the inductance of upstream converter. Okay. And this GS is parallel combination of this. So this is the second order transfer function. So it has some resonance here. So at this peak value, there is an overlap. Okay. From the previous lecture, we all know that that kind of overlap initiates the oscillation. So converter is unstable. So for this case, this might be okay, but this one is unstable. Okay, that is clear here. And I circled with this black curve. Okay, then we are connecting them together. So we are connecting like this. Then situation will be changed. Okay, so now it was GIU. Now it is GIL because this combination of this line filter and the downstream converter, it forms the load subsystem whose impedance is denoted as GL. So GL is here. Okay. Then this converter becomes load coupled converter, and you have this equation. This is input impedance of load coupled converter as given by this is input impedance of uncoupled converter. And we have two factors here, modification factor, and this factor is determined by the ratio of this and this, and the ratio of this and this. GOU is output impedance of this upstream converter. This is the regular output impedance, and GOU prime is output impedance of upstream converter. Evaluate with this input port open. Some strange output impedance, but we have this formula. Okay, so we are comparing. Now we are comparing impedances at this interface, which is denoted as interface B. So assume this. This is the GL. This is load impedance, and you have GOU, which is regular output impedance of upstream converter, and the GOU prime, which is the output impedance of upstream converter, plus this one, it really doesn't matter, upstream converter. Output impedance evaluate with input port open. Okay, so this is the typical case. Sometimes this becomes very small, so it disappears. But assume there is a 3. This impedance are bearing in this manner. So in this region, during this region, GL is very large. GL dominate, and in this region, GL dominate. Then this term will be gone. We ignore this. We ignore this. So this region, the GIL remain the same. GIU remain the same. Okay. So for that frequency, GIL is basically same as GIU. Okay. But in this region, in the middle part, GOU is larger than GL. GOU prime is also larger than GL. But these two terms becomes dominant. Okay. So for this case, GOU divided by GL, you are comparing GOU and GL. So there is this overlap, this much. It comes in the numerator. Okay. So you ignore this, then GIU will be increased by this area. Okay. Because of this. And there is another comparison. This GL and GOU prime. So this small one, I didn't shade this part. Okay, so this part is playing a role, but it is in the denominator, so it reduces the magnitude of this. Okay, so with this is the subsystem interaction at this point, and that affects the subsystem interaction at this point. Okay, so dynamic interaction here propagate to the upstream side. So interaction at interface B affect interaction at interface A. Okay, this is a very interesting problem. Okay, so there are stages of converter and filter. Some interaction will propagate upward or downward. So very complicated. We are trying to solve this problem. To analyze this problem, there is the one main object of studying this EET. EET is providing the formula, okay, best suited for our problem. So from this equation and this overlap, we know there is a boost of G in GIL from GIU by this amount, which is this overlap. This one triangular shape, something similar to triangular shape, and there is a drop from GIU this much. Okay, but this one is bigger than this. There is a net increase in the magnitude of this GIL from GIU. Understand this? Okay. So this impedance overlap is somehow translated the same thing. Okay, we separate this into the boost part and the drop part. Okay, and by some of this will affect this. So previously, when this is connected and there is a current sink and ideal voltage, so they are disconnected to individual converters. The lower one might be okay, but this one is unstable. But with connection, this input impedance of this converter changed from GIU to GIL. Okay, change occurs in this manner. So this area, this shaded area A is this one. A is actually this minus this one. So this is the net increase. Increase from GIU increase this much and it becomes GIL. Okay? With the load system connected, input impedance of this load coupled upstream converter is this one. Okay? Then this GS remains the same. Then GS is this one, and there is no overlap, so this much gap is present. Then this becomes stable. Okay? Previously it was unstable by itself alone, but somehow you connected this load with this, then this will be stable. Okay? So if you have some unstable part, maybe you can stabilize that part using this kind of propagation of subsystem interaction. Okay? Understand this now. Okay? So this is the message, and this is the detailed graphical illumination of that phenomena. So if you have time, you can go one by one, then you can understand this. Okay? So thing is, without this load subsystem, you have this, and you have overlap here. With this load subsystem, you have boost this much, and this blue curve is this input impedance of load coupled converter, and because of this, you avoid this, so it go around, it detours, so the overlap can be avoided. Then mill system can be stabilized. So this kind of phenomenon probably I found this phenomena, so I named the stabilizing load subsystem. So there is one paper, stabilizing effect of load subsystem. Okay, so that's one case. Right? There are many cases, this kind of application to propagate some interaction or completely stop the interaction, so we can control the propagation of some dynamics. The dynamics are moving around inside of the system, and you can install the stop or you can boost the interaction to have some good result. Okay, so all right, this is one thing. I have another example. This looks very complicated. Okay, sorry for this. All right, but the situation is very similar to previous case. So many things. Okay. All right. Try to understand every details. Try to understand the basic idea. Okay. The message I'm trying to convey you is the stabilizing effect of downstream converter, load subsystem. to the upstream converter. Okay, so you have one converter. This is converter. This is a boost converter, and this downstream buck converter. This is the current mode controlled buck converter, current mode controlled boost converter, and this is connected to the downstream, and this is the filter, line filter. Okay, but this is the bad filter, conventional line filter. Okay, so this system is unstable. But if you change this design, you modify design of this, then system becomes stable. The similar phenomena we observed in the previous lecture slide will occur here. Okay, so this is maybe not entirely practical, but very good example of this stabilizing effect of load subsystem. This figure was taken my paper, published about 10 years ago, like that. Okay, so let me try to illustrate this. Okay, all right. Let me explain from this part. So this is the interface A, and they are all connected. Okay, so this is the load coupled converter. This is also source coupled, but you don't have to pay attention on the source part now because we are comparing the impedance here. So we are separating this. So this is the load coupled converter, and this entire thing is practical load subsystem. Okay, we are comparing the impedance here. So GOF0 is output impedance of a filter with input shaded. Okay, so this is the typical way of evaluating the Thevenin's output impedance. Okay, so you kill this voltage source, you short this out, and evaluate this. That is shown here. So GOF0 is this one, very similar to the previous case, and this is the input impedance of this load coupled converter. Okay, so there is overlap, so system becomes unstable, and this is comparison. This is the polar plot of impedance ratio between this and this. Okay, this is the Nyquist plot, polar plot of this quantity. This is the ratio of impedances. Well, we can consider this as the loop gain. Okay, I'll explain that later in detail. Right? There is no loop, but this has the form of a loop. So this is the polar plot of this loop gain, and the loop gain does not encircling this one, but it dangerous approach to the vicinity of this. It goes near this point, so it is almost unstable. Okay, so this can be considered unstable, and there is overlap that indicate the system is unstable. So this is this link voltage waveforms. Okay, this is the hardware measurement. So it shows oscillation, and I was this current IO link current was 2 amp, and it reduced to 1 amp. Then the oscillation is gone. Okay, but very oscillatory, but eventually it settles down, and this current is again increased to 2 amp. Then oscillation is reintroduced. Okay, it's coming up again. Let me explain this. This low frequency part, this behaves as negative resistance, and that value is determined by ratio of this voltage and this current. When this current is large, it goes down. Okay, when current is small, it goes up. Okay, so with this small current, 1 amp current, it goes up, and overlap is gone. There's no overlap. Initially, it has overlap. So it has overlap. It shows oscillation in this link zone up. And when this current goes up, because this current is going down, okay, current is going down, then the R becomes large. Effective R becomes large, so it goes up. Then this oscillation is diminished like this, and later on it go back to this position, and the oscillation is coming up again. Okay. Problem with this design is this one. So we are comparing this impedance here at interface B. Okay. We are comparing GL and GOS. So GOS has this peak, sharp peak. This is because of this one. Okay. So system is at the brink of instability, and the sign of that it appears here. There's a large peak. Okay. So there is a large peak. Okay. So this is the bad sign. This indicates the system is unstable. Okay. If you analyze this, there is a RHP pole here. Because of this, then GL is much larger than this. Okay. So there is no impedance overlap. So there is no interaction in between. They are separated, but that is bad. Okay. So there is no separation. Okay. Then it won't change. Nothing occurs here because the GIL is related to GIU. This is very similar to GIU with this equation, but GL is much larger than this one and this one. Okay, this GOS is regular output impedance of upstream converter. GOS prime is input open output impedance of upstream converter. So there is a gap, large gap. So they are separated dynamically. So stability, actually instability, remain the same. Okay, that is the problem of this conventional line filter. As I said, the people, they try to provide the gap, large gap, to avoid the interaction between two systems, but this is the bad design because there is no stabilizing effect in here. Okay. So what we can do to stabilize this? Then we should have overlap here. Okay. If there is overlap, this will be modified. So this intersection here can be avoided. Okay. That is the basic idea. So this concept is very similar to the previous case. Okay. But this shows the conventional line filter. Okay. This is the way of people designing the line filter in the past. They are trying to avoid this, provide some impedance gap in between to have the dynamic separation. Okay. So, but that is the bad approach. So I modified this filter. So I call it stable. Okay, let me say one thing. Okay, so this DC link impedance is actually parallel combination of this and this. Okay, because the G link is defined at this point. So there are two impedances, one here. Then parallel combination of them is what? Is the G link, DC link impedance. Okay, so but one thing is very large. So GL is very large. This G link is the same as this one. We are comparing very small impedance, very large impedance. Then what we are seeing in the parallel combination is just small impedance. So G link is the same as this. Okay, so G link is this one, but this system is unstable. We have seen this. Okay, not this one. Here. Okay, so GS is the same as G link. G link is parallel combination of GOS and GL, but this guy is much smaller than the other one. So we are seeing is GOS. So this is the output impedance of this, and it is also the bus impedance, DC link impedance. There is no impact on the DC link dynamics, but with these new values of filter parameters here, this I modified this. Okay, I spent some time to find out this value. Then the result is this one. So GL is this one, and GOS is this one. this peak is GOS, and this is the GOS prime. So we have this equation, all right? So this one is boosting, okay? So we may have this sharp boosting, but we have this one. This is the dipping, okay? So increase this much, but decrease only this much, then this peaking will be gone, okay? Peaking is a bad thing, usually. So peaking is cancelled, and the remaining part is this one, this smooth one, triangular like shape, and we have boost in GIL here, and this overlap is avoided, okay? So with this, the same simulation, I just modified these values. So this is the current injection. So when this one is 0 amp, this was 2 amp, okay? No current is coming in from this DC link. When this is 1 amp, then it consumes 2 amp, so this current becomes 1 amp, okay? So this is the way of introducing the current step in the DC link. So for that case, this V link is stable, and it behaves this something like this, okay? Understand this. Try to understand this, all right? Okay, let me summarize this. This is a very interesting example. By using this propagation of impedance overlap or subsystem interaction, we influence the dynamics of upstream converter. We can stabilize upstream converter by introducing some gap overlap by proper line filter design. The inside of this converter remain the same. We don't touch inside of the converter. We cannot touch, and we don't want touch. What we are doing is just we redesign this one. Then this is the previous example, and with this new value, stabilizing line filter, we obtain this. Okay, so this is the previous one, and this is the new one. Okay. Sorry for this complication and confusion. Okay, don't be disappointed. Maybe you cannot follow this. Okay, but catch the basic idea. Okay, maybe it's too much for my YouTube audience, most of them. All right, another example. This is upstream converter, but for this case, this GOU and the GOU prime, the relative magnitude has been changed. Previously, GOU was this one, and the GOU prime was below this, but this is changed. This can occur. Depending on the topology and the control of this converter, this is the voltage mode control case, and the previous one was current mode control case somehow. Okay, that is very complicated to predict. That was not easy, very very tedious and very painful and very difficult. I have long derivation. Okay, with some approximation, I found this. If the voltage mode control, the position of this one, magnitude of this one has been swapped. Previously, this one was up and this one was down. Okay, for this case, this is the drop. Because this overlap, large overlap, comes in the denominator, so drop is bigger. This is the peak. Peak is smaller than drop, so it will propagate to this through this equation. Okay, then there is just this dip. Okay, previously it was like this, so there is a small overlap, small intersection. Okay, small crossover, but now this one is much bigger than previous one. Then what will happen? The system, this converter, becomes more stable, more unstable, because we have this small overlap, it was unstable. Small intersection, it was unstable. We have this large intersection, then system becomes more unstable. That is not the case, opposite direction. Okay. The important thing is this intersection occurs in the region where this input impedance behaves as minus RIC, which is the case of GIU here. So this is small, but this is unstable. Okay. Now you have large this much of overlap, but phase of this is something else. Okay. To have minus R characteristic, the phase should remain at minus 180 degree, but it is something else. Then still okay. Okay. So that is related with the Nyquist analysis, right? So this kind of example, not shown here. Ah, boy. Okay, let me go back this example. We have comparison here, okay? And I plot the polar plot of impedance ratio between this and this and this and this, okay? So it is almost touching each other. So this trajectory approach this critical point, very dangerous, almost unstable. But you have this gap, okay, large gap. Then this is well within this unit circle, okay. With the larger gap, this becomes smaller, and becomes more smaller. Then distance will reduce. Then it becomes more stable, right? So this is the case. Okay. All right. So this is the end of this lecture. Maybe this last example was too complicated and advanced story, but somehow I want to introduce this illustrate the use of this concept. Okay, so it really works. So with this, we can control the interaction to stabilize unstable system. Okay, and later on, use that. Using this kind of concept, you can program the performance of upstream converter, performance of downstream converter. So you can control the dynamics of remotely located power converter. Okay, so that is very, very interesting and promising. Okay, so let me finish up this lecture. So this is the last part of last lecture. Okay, let me stop here for this lecture.